Hello all, welcome everyone. This is Jyothika Ch pursuing BSc Final MPC in TTWRDC Women Kottagudem. I am going to discuss about thermodynamics. I will begin by outlining introduction of thermodynamics and highlighting the basic concepts of thermodynamics, and I will briefly explain about the laws of thermodynamics. The term thermodynamics, in that thermo means heat. Historically, it took lot of time to consider heat is a form of energy. In 1798, by Count Romford experiments, he explains heat is a form of energy. Later on, various scientists worked together and gave a thermodynamics to us. Thermodynamics is a branch of science, the division of science explaining the concepts of conversion of heat into work and heat into other forms of energy is called thermodynamics. This was formalized as a science by various scientists in the 19th century like Kelvin, Joule, Clausius, Clapeyron, etc., but Gibbs developed and endeavored the scope of thermodynamics into another level. Thermodynamics was originated as a result of man's endeavor to convert heat into work. It is a subject of great generality and it is extensively applicable to all branches of sciences and engineered to analysis of physical and chemical changes. Before going to introduction of my class of thermodynamics, let me ask few questions regards thermodynamics. When we rub our palms together, we feel warmer. When we keep a cup of tea in a room temperature, after some time it gets cool. Why? What's the reason behind it? Like this, many questions arises to us in our daily life related to thermo. Whatever the physical or chemical changes happen, that all comes under thermodynamics. Introduction of thermodynamics. Thermodynamics is a Greek word. Thermo means heat, dynamics means power or flow. The study of flow of heat is called thermodynamics. Now, the basic concepts of thermodynamics is thermodynamical systems, thermodynamic terms. System and surroundings comes under thermodynamic terms. Now, what is system? What is surroundings? It is defined as a finite quantity of matter or a prescribed region of a space upon whose observation or attention is there for analysis is called system. That means whose observation is there, that is called as system. And boundary. Here the term boundary means it is a actual or hypothetical enveloping, enclosing the system is called boundary. The boundary may be mobile or it may be steady. Everything in the universe except system is called surroundings. For example, if we take a water in a glass container, the water our observation is on water, so we consider it as system, and the glass container is called boundary, and remaining the air around the glass container is called as surroundings. System and surroundings together comprises a universe. That means the system and the surroundings is together comprises a universe. Now basics of thermodynamics, in that classification of system based upon the nature of boundary, systems are classified into three types: open system, closed system, and isolated system. In open system, there is a transfer of energy and matter between system and surroundings. Here in open system, the boundary we call it as volume surface. For example, automobile engine or the hot gas from the combustion and entering and leaving the gas turbines. In industries, we observe that gas turbines, in that the energy as well as the matter both will entering and leaving the turbines into system and surroundings. So we call that as open system. Next, closed system. In closed system, there is only exchange of energy takes place, not the matter. Such type of systems are called as closed system. Example for an closed system would be putting an ice pack on a injury. Here you observe, if any person will get injured, then ice pack will observe if we keep that ice pack on the injured part, the ice pack absorbs the energy and relieve the pain. Here what will happen? The energy will transfer but not the matter. So that called as closed system. And another example of closed system is a mixture of petrol vapor or air inside the combustion chamber of an engine. Now another system is isolated system. Isolated means, here the term indicates lonely. That means in isolated system there is no exchange of matter as well as energy. That means the energy and the matter remains constant in system and surroundings. Example for the isolated system is hot liquid in a thermal flask or a sealed vapor flask. These are the examples of isolated system. Here from the figure you can observe that in the first figure, open system means energy and mass or else energy matter both will entering and leaving the system and surroundings. That type of systems are called open system. And another one is closed system. In closed system only the energy may be transferred, not the matter. And in isolated system, neither energy nor matter, both are at constant, so it is called as isolated system. Next, in the basic concepts of thermodynamics, now we are going to discuss about thermodynamic variables. What is thermodynamic variables or equation of state? Thermodynamic variables, the variables which represents the state of a system, are called thermodynamic variables. Means, if a system, what is the state of a system? To explain that we use variables. That variables we call it as thermodynamic variables. For example, pressure, volume, temperature are called as thermodynamic variables, or also called as state variables, because the variables which are used to state the system, that only we call it as thermodynamic variables, so it is also called as state variables. Here the function of pressure, volume, temperature remains constant, and these three terms are independent. So if we know two values, then we can easily find another value by using the known two values, like PV equals to RT. Now, what is thermodynamic equilibrium? Here, thermodynamic equilibrium. We know till now thermal equilibrium. What is thermal equilibrium? If the temperature remains constant throughout the process, it called as thermal equilibrium. But here the term thermodynamic equilibrium means two systems when they are in chemical, thermal and mechanical equilibrium with each other, then we called it as thermodynamical equilibrium. From the figure you can easily observe that in the bottle there is water, and the water temperature is at room temperature and the surrounding temperature is also at room temperature. Both are in thermal equilibrium with each other, and the pressure inside the system, that means inside the bottle the pressure of the water, and outside the system, that means the pressure of the air, both are in uniform, so we called that as chemical equilibrium. Now mechanical equilibrium. Now the chemical equilibrium means the composition of water is H2O and it is uniform throughout the bottle, so it is in chemical equilibrium. Any system which is in thermal, chemical and mechanical equilibrium, then we call it as a thermodynamic equilibrium. Here the bottle contains thermal equilibrium, mechanical equilibrium and chemical equilibrium, so it is treated as thermodynamical equilibrium. Any system, not only this, any system, if it possesses thermal, chemical and mechanical equilibrium, then the system is said to be in thermodynamical equilibrium. Now coming to thermodynamic process. What are thermodynamic process? There are four types of thermodynamic process. They are isovolumeric, or also known as isochoric process, isothermal, adiabatic and isobaric process. What are these processes? First one is isovolumeric or isobaric process. In this process, in thermodynamic process, throughout this process, the volumeric or isochoric means volume, the volume should remains constant, or the volume should be uniform throughout the process. That process we call it as isochoric or isovolumeric process. For example, a car with closed window parked in a hot garage is an example of a isochoric process. Means throughout the process the volume should be remains constant, but it will be in thermodynamic process only. And here volume is constant means no work done on the system or by the system. Why means we all know that work is equal to PdV, means pressure change in volume. Here the volume is constant means change in volume do not occur, so work done is equal to 0. So work done on the system or by the system will always 0 in isochoric process. Next, isothermal process. In isothermal process, throughout the process the temperature will be remains constant. That type of processes are called isothermal process. Example of isothermal process are slow process like a balloon expanding slowly during the day is an example of isothermal process. And adiabatic process. What is adiabatic process? In adiabatic process, throughout the process the heat remains constant, no exchange of heat will takes place. That type of process are called as adiabatic process. Adiabatic process is also called as isolated process also. Example for adiabatic process are fast process like filling a tank is an example of adiabatic process. Next, isobaric process. In isobaric process, throughout the process the pressure will be remains uniform. That means entire the process the pressure will not change. This process is called isobaric process. Example of an isobaric process is heating an open pot of water. Here, if you observe that a graph is plotted between pressure and volume. Y-axis plotted as pressure and x-axis plotted as volume. Here, first one is isobaric process. In isobaric process, we get that horizontal straight line, because in isobaric process the pressure will remains constant, so we get a horizontal straight line. And then isochoric process, in isochoric process or isovolumeric process, the volume will be constant, so we get a vertical straight line. And isothermal process and adiabatic process, the curves get slightly curved, bent, because in isothermal process and adiabatic process the pressure and volume changes will occur like that. So from the figure it is observed that how the process will occur. And next, work done in an isothermal process. Work done in an isothermal process, we all know the work is integral form of PdV. So here P means pressure, V means volume, and change in volume we denote as dV. From the ideal gas equation, PV equals to nRT. Here P means pressure, V means volume, N equals to number of moles, R is universal gas constant, and T is absolute temperature. From that we write P value. P equals to nRT by V. We considered first W equals to integral of PdV as first equation, and now this P value is second equation. By substituting second equation in first, W equals to integral of nRT by V dV. Here N and R and T are constants. In isothermal process, temperature constant. So nRT we take it as from the integral form. So integral initial volume to final volume 1 by V dV. Integral of 1 by V is log V. We all know that. By substituting the upper and lower limits, log V2 minus log V1. Log A minus log B, we have the formula log A by B. So nRT log V2 by V1, we get this as work done in an isothermal process. Next, work done in an adiabatic process. Work done in an adiabatic process is what? Work done in an adiabatic process, PV to the power of gamma equals to K. In adiabatic process, we considered K equals to PV to the power of gamma. And P1V1 or P2V2, anything we can consider. It depends upon the states. So W equals to PdV, we all know that. Here from the K equals to PV to the power of gamma, we can derive the P value. K by V to the power of gamma we get. By substituting the P value in work done, W equals to integral of PdV, we get P2 V2 gamma minus 1, V to the power of gamma minus 1, and P1 V1 gamma and V2 gamma minus 1 by 1 minus gamma. From this we can write 1 by 1 minus gamma P2 V2 minus P1 V1. From the ideal gas equation we know that PV equals to nRT. So by here two states are there. So P1 V1 treated as mu or T1 and P2 V2 treated as mu or T2. By substituting these values, W equals to 1 by 1 minus gamma mu or T2 minus mu or T1. Here the terms mu and R are constants, so we take it as out as common. Mu R by gamma minus 1 T1 minus T2. This is the work done in an adiabatic process. Next, difference between heat and temperature. Most of the people assume that there is no difference between heat and temperature. These two terms are same, but no, they are all not right, because heat and temperature both are different. There is a difference between heat and temperature. Heat is a form of energy. Temperature is its measurement. To measure how much heat of your body, we use the term temperature. And heat raises the temperature of your body, but temperature decides how the heat will flow from high temperature to low temperature. It will decides. And heat is a measure of joules, and temperature is measured in terms of kelvins or Celsius. Like in physics we have derivations, right? Mathematics we use for the derivation part. Mathematics is a language to express physics. Like that, temperature is a measure to express heat of a substance. Like that, there is a difference between heat and temperature. Next, temperature and zeroth law of thermodynamics. By zeroth law of thermodynamics, we define temperature, we define heat. Fowler, the scientist Fowler proposed this zeroth law of thermodynamics. Actually, what will happen means, first scientists proposed the first law of thermodynamics, then second law of thermodynamics. But after that, Fowler proposed the zeroth law of thermodynamics, and he felt that by using this zeroth law of thermodynamics only, we define temperature. Temperature is the basic one to express all type of heat of your systems or substances. So they already named as first law and second law. So he named that law as zeroth law of thermodynamics, because before 0 is there, so he named it as zeroth law of thermodynamics. And from the zeroth law of thermodynamics only, temperature concept will rise. The zeroth law of thermodynamics signifies the temperature of a system. So from this, heat, temperature will came into the picture. What is heat? What is temperature? We all obtained from the zeroth law of thermodynamics. Heat is a form of energy, and it transfers between the substances due to the difference between the temperatures. Heat always flows. Objects do not have heat. The point here make you little bit confusion, but if you observe clearly, heat flows always from objects which do not have heat. Means if for example, if we keep a hot teacup in a room temperature, the air which surrounds the teacup will be at normal room temperature. So it is in, when compared to the teacup, it is in cool temperature. So always the heat wants to transfer from high temperature to low temperature, and which doesn't have the heat, the substance which doesn't have heat, to that only the heat will transfer. And then heat always transfers from high temperature to low temperature until it attains thermal equilibrium. Because when the two objects, or when the two system or surroundings, whatever, when the two systems are in thermal equilibrium, that means there is no transfer of energy between two systems. That means they two are in same temperature. Until that point, they will transfer energy. For example, again we take one hot substance and we keep it in a normal room temperature. The air surrounds that hot substance will be at room temperature, so it gains heat from the hot substance until the hot substance and the air surround it will be in thermal equilibrium. So like that, the heat transfers until the two systems, or the system or surroundings, or the two substances will attain thermal equilibrium. Now, zeroth law of thermodynamics. What is zeroth law of thermodynamics? From the figure, you observe that we have three systems or three objects A, B, C. Here, A, B and C, the objects A and B are separately and independently thermal equilibrium with the third system C. That means A is thermal equilibrium with C and separately B is thermal equilibrium with C. But here A and B is also thermal equilibrium with each other because there is no contact between A and B. But A is thermal equilibrium with C and same temperature. A have the same temperature like C and B also have same temperature like C. So A and B are also in thermal equilibrium with each other. This is called zeroth law of thermodynamics. From this zeroth law of thermodynamics, we define the temperature and we came the concepts of heat and temperature. Now next, basics of thermodynamics. Before going to first law of thermodynamics, we discuss about the internal energy, because in first law of thermodynamics, internal energy is the key one. By that internal energy only we can explain the first law of thermodynamics. So what is internal energy? It is defined as the sum of the kinetic energy of all particles and sum of the potential energies of interaction of those particles. That means change in internal energy equals to delta U equals to, here delta U equals to change in internal energy. U2 minus U1 is U1 is initial internal energy and U2 is final internal energy. By the difference of this only we can estimate the internal energy of the system. Internal energy is nothing but, for example, if we take one gaseous substance, in that the molecules are always randomly movable. The kinetic energy of that molecules and the potential energy of those particles, we can sum up them, then we get the internal energy of the system. By using the internal energy of the system, we can explain the first law of thermodynamics. What is first law of thermodynamics? First law of thermodynamics is simply, we can say, the amount of heat energy we are given to the system, it is utilized to increase its internal energy, and some of that is utilized to be work done. For example, from the figure you can observe that state 1 and state 2, in this pistons, in the container the pistons are there. From this state 1 to state 2, the heat will transfer and the work done will also occur. The work done, how the work done will occur means, in state 2 you can clearly observe that one of the piston will raises up. By that the gas will work done on the system, it will explains. Here internal energy, we denote here internal energy as E. From the state 1 and state 2, E2 minus E1, because we just now we discussed internal energy delta U equals to U2 minus U1. Like that here E2 minus E1 equals to the amount of heat energy, here denote as Q, and the work done is W. Change in internal energy is equal to the difference between the heat transfer into the system and work done by the system. This is called first law of thermodynamics. Means here what will you will observe means, change in internal energy equals to difference in the transfer of heat energy into the system. That means from the state 1 to state 1, state 2, and work done by the system. Here the piston will arises. So in the state 2 you observe that the gas will do work. So by the system it will happens. That means first law of thermodynamics, what the first law of thermodynamics states means, the amount of heat energy we given to a system is somewhat utilized to increase its internal energy, and work done by the system. This is called first law of thermodynamics. Limitations of first law of thermodynamics. First law of thermodynamics, just now we discussed the first law of thermodynamics, but in first law of thermodynamics some of the drawbacks are there. What are they? For example, they didn't explain the what conditions or processes or phases. For example, in first point you observe that from the figure, fuel to work, that means by converting fuel energy into work, we can convert fuel into work, but the process is not irreversible because that work can't again convert into fuel. It is the process is not occur. So first law of thermodynamics doesn't explain the process of how from fuel to work or work to fuel. Like this, it doesn't explain the processes, how if the process will occur like that, means how the first law will obey, like that some of it can't explain by the first law of thermodynamics. And second one, it also doesn't explain whether the process will occur on its own or not. Here the second one is, from the ice to liquid, the conversion of ice to liquid will happen as spontaneously on its own, but it can't again converts liquid into ice spontaneously or without external work. By doing external work only it can convert again liquid into ice. So it is not possible for the spontaneous or like this process. What will happen? The first law of thermodynamics doesn't explain. And again, it also doesn't explain the conditions, whether how, if for example from high temperatures to low temperatures always the heat flows, but what about the converse, from the cool regions or from the cold substances to hot substances, the energy will transfer or not? Then what happens to first law of thermodynamics at that conditions? Like this, some of the process, phases and conditions doesn't explain by the first law of thermodynamics. So to rectify these drawbacks or these limitations, second law of thermodynamics came into picture. What is second law of thermodynamics? In second law of thermodynamics there is two statements, and the two statements is given by the great scientists Clausius and Kelvin Planck, and they named as Clausius statement and Kelvin Planck statement. What is Clausius statement and what is Kelvin Planck statement? Clausius statement is, it is impossible to construct a device that transfers heat energy from a cold reservoir to hot reservoir without applying an external work on it. That means without applying any external force on a substance, there is no flow of heat from a cool region to hot region. It is impossible thing. That statement is given by Clausius. And Kelvin Planck statement is, it is impossible to convert the heat energy, whatever the heat energy we are given to the system, it is impossible to convert the heat energy completely into work. Somewhat of energy what we are given to the system, that is must and should utilize it to increase its internal energy, and remaining part should be converted into work. And this was given by Kelvin Planck statement. Kelvin Planck statement is, it is impossible to a device operating heat engine, the effect of which is to absorb energy in the form of one object from a singular reservoir and to deliver the whole energy, whatever the heat energy given to the system is, into work. Example for the Clausius statement is refrigerator, because in refrigerators, by applying external work, that means by giving the electricity only, we get the cool in the refrigerators, we get, by abstracting the heat in the backside of the refrigerator, by abstracting that heat only, we get the coolness. So it is an example of Clausius statement, and Kelvin-Planck statement is the heat engine. It is the further in heat engine what happens, whatever the source working substance sink we take, that amount of heat energy coming from the source will be utilized to increase its internal energy, as well as some of the heat energy we given to the system is utilized to convert into work. So this is called these two statements all comes under second law of thermodynamics. Why second law of thermodynamics came into picture? Before only I explain, in first law of thermodynamics what happened, in first law of thermodynamics explains the certain amount of energy flow in particular system or in particular conditions or in particular process. That means the amount of internal energy we are given to the system is completely change in heat. That means the amount of change in internal energy or change in work done is equal to heat energy. But what happens when the conditions or when the process or when the phases are changed, it can't explain. So to explain that, second law of thermodynamics came into picture. By second law of thermodynamics, we can if the processes are reversible or irreversible, or the conditions maybe the from cold region to hot region or hot region to cold region, and also spontaneous reaction, non-spontaneous reactions, whatever the reactions, whatever the phenomenons, all should explained by the second law of thermodynamics. In second law of thermodynamics, there is a main wonderful concept is entropy. Entropy means disorder of a system or randomness of a system. By that also lot of changes will occur in thermodynamics part. And next is in second law of thermodynamics, direction of change. How the direction of change? In second law of thermodynamics, the process will occur in a certain direction and the energy has quality as well as quantity. Always in second law of thermodynamics, the energy the transformation of energy took a some direction, means always it transfers that the heat energy transfers from hot reservoir to cold reservoir, not from the cold reservoir to hot reservoir, because to extract or to transfer the heat energy from the cold reservoir to hot reservoir, by applying external work only it will happen. That is only in our Clausius statement, like that it will happen. So by this my class is completed. Before end up my session, just I will summarize what we are discussed in this class. Firstly, we discussed the introduction of thermodynamics, later on basic concepts of thermodynamics and laws of thermodynamics, limitations of thermodynamics, and how the thermodynamics will useful. Thermodynamics is a great generality of subject to express the phenomena around us, and it is widely extensively used in all branches of sciences and engineered to analyze the physical and chemical changes all over. So thank you all. I hope you all understand. Thank you for the listening. Thank you.